Hi, let me spend some time to explain the binomial probability distribution because this is the foundation for the calculating reliability for the parallel system. Okay, so to some of you this could be a review, to some of you it could be something new, but either way I try to make it as intuitive as possible. So binomial probability distribution that help you calculate the probability that fits certain description. It doesn't help you calculate everything. It only helps you figure out that the certain type of events that fits into its description. What are the descriptions? Which I'm going to explain now. Okay, so in binomial distribution, we're simplifying all outcomes to only two cases. Okay, you may have many different type of outcome. Each outcome can be labeled as 1, 2, 3, 4, 5. No, in this case, we're only considering event will be able to classify its outcome into two different type and two different type only, failure and success. Not that because it has a negative consequences, therefore we're calling it as a failure. It's that sometimes we have the focus, the event that we'd like to observe. And the event that we'd like to observe is the success event. For example, in case of considering customer make a purchase is our focus in terms of observation. Therefore, we call it as a success event. If customer did not make a purchase, we call it as a failure. Okay, so if you're considering 10 vehicles driving down the road, if you'd like to learn the probability of failure, even failing transmission is a negative consequences, but we still call it as a success event as long as that's something we'd like to observe. Okay, and therefore it is binomial because whatever outcome, you're only trying to classify them under two different names, success or failure. That's a name you're given to the outcomes. Okay, and then we are considering a situation where you are observing n concurrent events, the events that are happening at the same time that are not related to each other. Okay, again, it is independent assumption. The car 1 failure rate has nothing to do with the car 2 failure rate. Okay, things like that. In each case, the probability of success is constant at P. So it means all the vehicles, all the customers, all the units, all the events that you're considering has the same probability of success at P. Therefore, the probability of failure is 1 minus P. Okay, are you ready? I'm going to show you something. Okay, it looks monstrous, but it's really not that bad. Okay, so the probability of observing exactly X success. Make sure you understand this correctly. The probability of exact X number of success. Okay, that's what we're trying to calculate. So what is this? This is called binomial coefficient, which I'm going to explain to you later. And p powered by x and 1 minus p powered by n minus x. So a simplified version is n choose x, p powered by x, and so forth. Let me show you what this is, okay? Let me show you what this is. So this is a simple example. Exactly 2 out of 3 customers make a purchases when each customer has a 60% chance of making a purchase. So let's think about this. Okay, what is this? This is what we're trying to figure out. Exact 2 purchases out of 3 customers. So when you have 3 customers walk into the store at the same time, what happens? Okay, you can open up your imagination, but 3 customers walk into the store and there are 8 different possibilities under the lens of binomial probability distribution. These are all possible scenarios I presented here. So if you think about it, the first customer may make a purchase, next customer may not make a purchase, third one also may not make a purchase. Okay, you can draw something like this. First one did make a purchase. Second one also made a purchase. Third one also made a purchase. Like this, right? First one did not make a purchase, and so forth. So it's 1, 2, 3, 4, 5, 6, 7. Total, we have 8 different scenarios here. This is what you're seeing here. Okay, so our description is we are interested in calculating exactly 2 out of 3 can make a purchase. So let's review each scenario and see whether each scenario fits our description. Number 1 does not. Number 2 does. Number 3 does. Number 4 does not. Number 5 does not. 6 does not. 7 does not. 8 does. Okay? You see, why 4 does not? Because this is calculating the probability of 3 out of 3 make a purchase, which is not our concern. We're only concerned about exactly 2, like this case. Right? Like this case. The scenario number 2 has customer 1 and 3 made a purchase, 2 did not. Scenario number 3 says number 1 and number 2 customer made a purchase, 3 did not. Scenario number 8 is last 2 customer made a purchase, first did not make a purchase. So there are, out of 8 different scenarios, there are total 3 scenarios that fits into our description. Therefore, we'd like to multiply the probability of 2 customer made a purchase, 1 did not make a purchase. Okay, intuitively, this is probability of 2 made a purchase, 1 did not make a purchase. However, we have found out there are 3 cases this can happen, or the order could be different. But we are observing actually 3 things like this is happening in our scenario. So that is the reason why you see this thing right here. Okay, this is the binomial coefficient. We're 3 choose 2 here. Okay, and exactly there will be 3 events like that will happen. 3 scenarios like that will happen, and if you think about this closely, this is nothing but this. Okay? The probability of success powered by the number of success events we'd like to observe, probability of failure, and number of failure events we'd like to observe. So if you're trying to link this formula with what we have done here, you can actually link it easily. Okay, and if you're wondering how to calculate this part quickly using Excel, the combine formula can help you do that. This is combine 3 choose 2. Okay, there will be cases where you need to do much more complicated, combination calculation. For example, you'd like to observe exactly 6 out of 10, right? When each component has a success chance of 60% and things like that. So in that case, what you need to do is, 10 out of 6 powered by 6, 0.4 powered by 4. Okay, it's quite easy because the binomial probability distribution can give you a tool and a structure that can help you easily calculate something that may look very, very difficult to solve at the first place. Okay, so with that in your mind, let's move on. To make this even more useful, we can actually construct a table like this. Construct a table like this. Oops, okay, like this. So what is this? I am enumerating all the possible probabilities here. Okay, so when you have a total of 3 customers, you can never have more than 3 customers make a purchase at the same time. Okay, this is what you're seeing here. But you can still have nobody is making purchase, only 1 making purchase, 2 made a purchase, 3 made a purchase, right? But you cannot have 4 made a purchase when there is only like 3 customers in there. So the total number of events is the maximum number you can put here. Okay, and this one shows the Excel solution. You can utilize the binom dist to calculate the the monstrous, you know, this formula. So you can, instead of using, sorry, this is a mistake. Instead of using your calculator, you can just use Excel to conveniently calculate this. Okay, so as you can see, this is quite convenient. Let's move on, and I'd like to demonstrate one last thing in this particular component. Yeah, this is a different example, I think. In this case, you are considering 8 different events. Each has a success chance of 30%. Okay, I have constructed the binomial probability distribution in its entirety for this exact case. Okay, so what does it tell you? The chance, where the setting is this, exactly 0 made a purchase, and exactly 0 success out of 8 events is this. Exactly 1 success out of 8 events is this. Exactly 2 success out of 8 is this, and so forth. So you can enumerate all of them. Okay, this is again the Excel solution. Look at the Excel solution closely, and once you got this, you can easily develop a histogram based on this. Okay, of course it resembles a normal curve again. Okay, so binomial, when you're considering huge number of concurrent events, and it kind of becomes very, very difficult to do this calculation. Okay, so in that case, we sometimes, when the number of n is large enough, we basically use normal distribution to estimate the result and outcome. Okay, this is just another example that show you how to develop a binomial probability distribution. So I think I'd like to stop here before I jump to the next example. Yeah. I hope this served a good review for the binomial probability distribution part.